Good morning, sir. Our session speaker has joined. It is my pleasure to inaugurate the day 6 of the faculty development program. I hope Aragu sir is ready to give the introduction for the speaker here. Aragu sir, can you check your mic, please?
Yes, sir. Am I audible, sir?
Clear and audible.
Yes, sir.
You may please proceed with the introduction of the speaker here, sir.
Good morning to one and all present for this 11th session of 6-day virtual faculty development program. It's given me an immense pleasure to warmly welcome today's distinguished resource person, Dr. Raja Kumar, to this faculty development program. Dr. S. Raja Kumar is currently serving as an associate professor in the Department of Manufacturing Engineering, Annamalai University, Tamil Nadu. He is a UGC Research Awardee and DST Young Scientist Awardee, which clearly reflects his strong academic and research credentials. He obtained his PhD in Manufacturing Engineering from Annamalai University, with his doctoral research focusing on the effect of friction stir building process and tool parameters on the quality of the aluminium alloys. He also holds an ME in Production Engineering and BE in Mechanical and Production Engineering, both from University. Has professional experience of over 16 years in teaching, 13 years in research, and 2 years in industry. His areas of specialization includes manufacturing engineering, material joining process, optimization techniques, and surface engineering. He is 109 reputed international journal publications and over presentations at national and international levels. Notably, such articles has been recognized as the hottest articles in Science Director. So serves as a reviewer for several high-impact international journals published by Elsevier, Springer, ASTM, and other reputed publishers, and has received Outstanding Reviewer Award from Elsevier. Dr. Raja Kumar has successfully guided numerous PhD research scholars, many of whom are now contributing significantly to academics and industry. His teaching portfolio spans a wide range of UG and PG courses, including engineering metallurgy, material science, welding and joining process, composite materials, tribology, nanomaterials, and surface modification techniques. This vast academic experience, strong research background, and his practical insights into the advanced manufacturing and joining technologies, we are confident that will be highly informative, insightful, and inspiring for all the participants. On behalf of the WellTech Multitech, Dr. Rangarajan and Dr. Shakuntala Engineering College, and all the participants, I once again extend a very warm and heartfelt welcome to Dr. S. Raja Kumar, and we look forward to an enriching session today. Thank you, sir. We welcome you.
Sir, can you please repeat the number of publications and his citation count, sir? It was a disturbance.
Sir, 109 publications in reputed international journals, sir.
Yes, sir. Sir, sorry for the small interruption in the beginning, sir. Dr. Rajakumar, sir, I am very indebted to you for guiding me through my research journey. This is my opportunity to tell my gratitude towards my research journey. And currently, I am serving as professor in WellTech Multitech Engineering College, sir. Sir, you may share your screen, sir. Shall I stop your my presentation? Okay, you have taken over. Thank you, sir. Thank you, sir.
Is it visible?
Visible, sir. Your voice is also very clearly audible, sir.
Okay, good. Thank you for your nice introduction about me. So, first of all, I would like to thank Dr. Muthukumar for giving a nice opportunity to share some of our findings in this online FDP program. So, I'm very happy to share some of our research work in this forum. So, today I am going to present the novel topic, which is most of the researchers are more interested on doing research in the exotic materials by using probably most of the researchers are focused on they are aware of the friction welding processes. But additional to that, so I want to share the new upcoming processes like some of the conventional welding process. I'm not keep it in touch on the whatever the previous whatever the availability power sources. Just I want to share the one more important power source which is available in our laboratory, because I was received this machine from the Fronis India, Austria. So under the DST ANR project. So so that today whatever the work is delivering today, whatever the work is. First one is efficiency building. It is my PhD work, and the remaining topics one of my scholar is doing now. So probably he will be submitting his thesis another couple of months. So I hope these lectures will you have to enjoy. So so I am starting with the first process. So it is one of the important process in nowadays, that is called the friction welding process. So why I am saying that it's a novel or innovative process is that, so you can see that, so whatever the aluminum or the non-ferrous materials, so it is very difficult to weld in the conventional welding processes. So first we should know that what is conventional, what is solid state welding processes. So solid state welding process is nothing but the welding is taking place within the solid state itself. There is no melting take place. So within this, we have to make it a joint. So whereas in the case of the conventional welding process, the melting has occurred, then it will be adding with some filler wire, or without filler wire, you can join together. That is the major difference between the conventional welding process and solid state welding process. First, I will I will maybe discuss the one or two processes related to the solid state welding process, and then we can move on to the one more process like the conventional welding process such as plasma welding process. That is why I am telling that plasma is, you can hear that process, but in our machine, it is exclusively designed for the from that power source. You can make it for the thin sheet, thick sheet, as well as the even beyond that 10 mm thickness. You can do it welding without the filler wire. That is the main novelty of the keyhole plasma welding process. Or sometimes, suppose you can do it in the thin sheet, then it is called as microplasma. Or you can go to the 2 to 6 mm thickness, then it will be called as soft plasma. Then you can go 8 to 10 mm thickness, it is called as keyhole plasma welding process. All the three process, we can do it on the only one single process, that is called as plasma arc welding process, which is available in our center. Right. So first we can see that the one of the important process like friction welding process. You can see that the process title itself, it has friction, right? So friction is nothing but when you are rubbing in two hands, what will happen? Because of the friction, the heat is generated. Similarly, you can look into the process, right? The friction welding process. Two kind of it may be called as tool, or it may be called as a workpiece. It has rubbing or stirring over the two surface contact area. It generates the volume of heat, right? That heat is sufficient to plasticize the material, so that it is called as still welding processes. Right? You can see that. So this process is invented by the Welding Institute in the year of 1991. So already told that it is the solid state welding process. In that welding, the material does not recast, or probably there is no required for the melding, there is no required for the filler wire, so that it is called as shear and autogenesis process. Because of that, you can see that it is a environmentally cleaner welding process, because it will not produce any smoke or fumes or glare. So it is, if it is not possible for the smoke or fumes, what will happen? The welder has to be he will not affect any respiratory issues. That's so that this process is universally accepted for the environmental cleaner welding process and also the pollution free. You can see that this image, it is that is the tool. The workpiece has to be, one side is called as advanced side and another side is, because we are making joint is two plate. So one is you had to fix it in the advanced side and another one is kept as the radiating side. It is the non-consumable tool. So why it is a non-consumable tool is the general thumb rule for to making it a tool is that, so normally the tool metal is harder than the workpiece. That is the thumb rule for whenever you are, suppose in case if you are making welding in the aluminum alloys, you can go for the steel, right? Whether you can go for the high carbon steel or high speed steel, right? Like that you have to make it. Or you can go to the titanium or steel, then you can go for the tungsten carbide tools, right? So many of the tool materials are developed recently. So when we were working in the 2011, so at the times only for most of the researchers are only focused on the non-ferrous alloys alone. So there is no work on the steels. Now most of the steels and other hard materials also possible to weld from this process. So, but as per my suggestion or as per the literature says that this process is more predominant to the non-ferrous alloys, especially for the aluminum. So aluminum is the very challenging one in the to weld in the conventional welding process. That is the aluminum oxide. So the aluminum oxides end up with the crack or some porosity will occur during the conventional welding process. Probably you can go for the thick welding process because of high heating and melting. So it end up with the porosity. So to avoid those issues, you can go for this kind of process, that is the efficient welding process. You can now, most of the aerospace industries, Boeing, they can utilize or use it for the efficient welding process, right? So already told that. So normally the conventional welding process, it has only three distinct zones. One is for the fusion zone, and another is the heat avoided zone, and third one is the base material, unabated base material. But you can see that in this process only, it has one more region is actually added, that is called as thermomechanically affected zone. It is mainly happened because of the tool and the pressure and the workpiece. Right, so that it is called as thermomechanically affected zone. So you can see that what are the process parameters are important of this process is that. So first one is the rotation speed, the tool rotation speed. It is it may be generate the heat, right? So if you are the lower rotation speed, so always gives the low heat input. So higher rotation speed, so it will give the high heat input, vice versa. You can see that in the welding speed is a inversely proportional relationship to the heat input. What will happen? So low heat input, it gives the low welding speed, it gives the high heat input. So higher welding speed, it gives the low heat input. So axial force, it is a tool plunging. So when we are giving the force towards the workpiece, so the axial force also it's playing a vital role. So if you are giving more axial force, the metal has to come out more. So you have to maintain the axial force. So according to your material, then the other three parameters are related to the tool parameters, like the tool pin profile, shoulder diameter, and tool tilt angle. So normally you can fix the tilt angle is 3 degree or 4.5, right? It's a maximum of 4.5, so the best results you can get it. So not only the tool tilt angle, even you can the tool metal harness also playing a vital role. So you can measure the tool metal harness and the pin profile. So it has a variety of pin profiles are there, but universally recommended that the threaded pin profiles gives better mechanical properties when compared with the other pin profiles. right? This is the equation for to calculate the heat input. So you can see that the higher heat generation, it already told that higher rotation speed, lower welding speed, high axial force, higher shoulder diameter, radius, and the high mu coefficient of friction, that is called as it depends upon the relationship between the tool metal harness. If you are the higher heat input, what will happen? So the turbulence of the metal flow will be high, and what will happen in the metallurgical aspect? The grain coarsening will take place, and precipitation, agglomeration, and possibly we can see that because of high heat generation, what will happen that the excess flash formation will be happen, and formation of the defects such as some of the defects like piping defect, tunnel defect, kissing bond, right? Some of the defects will also form when increasing the heat input. So whereas you can see the low heat input generation, so what will happen is that, so it is mainly related to the low rotation speed, high welding speed, low axial force, the lesser shoulder diameter, and the harness of the coefficient of friction is lesser. What will happen? So there is no vertical flow of material takes place, and it deteriorates the poor metal consolidation and formation of the defects such as pin, holes, kissing bond, lasers, cracks, maybe end up with the by the low heat input generation. So we have to optimize the heat generations. How we can optimize? So we have to we have to make it a trial and experiments, and then we can optimize the above parameters. Then only we have to suitable for to proper welding. So if proper welding takes place, that is called that maybe it has a proper material flow and good consolidated of weld metal defect-free welds. So you can see that video. So we have the facilities. It is not the CX welding machine. It's a conventional welding machine. So vertical milling machine. From that we have to convert into the welding process. So you can see that this is the tool. You have to properly clamping over the workpiece. Then you can see that the tool is rubbing over the workpiece. The tool is extracted, right? So you can see that the flash formation really depends upon the excessive heat input. So you have to remove the excess flash formation. It is already told that it is mainly suitable for the aluminum alloys and the magnesium. So they're probably non-ferrous alloys. So first you can see the one of the case studies in the this process. So this work is to study the effect of friction welding process and tool parameters on weld quality of aluminum alloy. So in this work, I have been chosen for the aluminum 7075. The condition is at T6. Why I am choosing this material is that it is a high strength aluminum alloy. So this material is used in the aerospace applications. As you can see that the panel, the wings, everything it has to be made by the aluminum 7075 alloy because of the lightweight and high strength. It is equal to the steel. So and the importance of this alloy is the corrosion, or corrosion is very less when compared to the other materials. Cost wise is also cheap. So you can see that the chemical composition of these alloys, the maximum is the zinc 5.1 and the magnesium is 2.1, and then silica is 0.63 and copper 1.2. And the mechanical properties of these alloys, it will give the maximum ultimate tensile strength of 485 megapascal and harness of the biggest harness of 160 HP. Sorry, you can see that. So I have chosen for 3 alloys, right? So one is the pure aluminum alloy, and second one is the medium strength, that is 6061 and 7075. You can see that the 7075 I am given a presentation only in this 7075 aluminum alloy. So you can see that the grain boundaries are coarse and elongated grain boundary with the same image, you can see that the dimple size also goes on longer. So you can see that the dual dimensions, we can use it for the high garment steel. So the another thumb rule for to fixing the dimension of the shoulder diameter and pin diameter and the length of the pin diameter is mainly depends upon the thickness of the working material. You can see that. So in this work, I am using for the 6 mm thickness of the 7075 aluminum alloy. So once the length of the pin is, you have to fix it for the 80 to 90 probably. So universally, the welding institute is recommended for the 80% sufficient for to fix the length of the pin, because if you are keeping more 80 or 90%, it will go bottom of the plate. So that you have to maintain for the 80% of the pin length is sufficient for to make the joint. And the diameter of the pin is, you can make it as the whatever the thickness, right? You can make it. So for example, so if you have the thickness of the 6 mm thickness of the aluminum plate, then the diameter you have to keep as a 6 mm diameter. Then the shoulder diameter you have to make it as a 3 times of the thickness of the plate. So for example, if you are taken to the 6 mm of thickness of the plate, you have to maintain the shoulder diameter is the 18 mm of diameter. The length is 80%, right? That is a thumb rule for when you are choosing for the tool pin profiles, tool pin diameters. So you can see that. So another, that is a machine for, we have it 2 machines. So the first one videos you can see in the conventionally, that is vertical milling machines, and this one is the specifically indigenously designed for the for example, you can see weld in the even the steel also, right? So it is a CNC machine. See, in our department we have this facility. This is a shoulder holder, and we have to keep the tool, and this clamping device is required for to keep the material proper clamping. So this is slide shows the fabricated joints of the Piro aluminum alloy and 6061 707 alloy. You can see that the what is the effect of process parameter on the mechanical properties and corrosion rate and grain size of the 70 high strength aluminum alloy is that. So because I am studying for the what is the effect of the rotation speed on tensile properties and corrosion and grain size, because corrosion also playing a vital role in the design aspects. So we in that work we have to optimize for the low corrosion as well as the better mechanical properties. You can see that the rotation speed we have to keep in as the 5 rotation speed, 1200 RPM, 1400 RPM, 1600 and 1800 RPM, and we have to conduct the test, and we have to record the results, record the values of the tested samples, like tensile hardness, corrosion rate, and grain size also we have to measure. And you can see that. So for example, 1000 RPM rotation speed, it gives the better mechanical properties when compared with the 1200 and 1400, 1600 and 1800. So I will explain why it gives the better mechanical properties when compared with the other variables. Similarly, you can see that we have to capture the image, the cross section of the macro. So after welding, so we have to polish it, and you can go for the stereoscope microscope, and we have to visually see the how the macros or size of the macro, right? We have to measure it, right? You can see that. So the rotation speed of 1000 RPM, the heat input is 420 joules per mm, and the tensile strength is 283 megapascal, and weld hardness is 156 Vickers hardness, and corrosion rate corrosion rate, we have to measure the immersion corrosion test. So you can see that 8.4 into 10 to the power minus 4 mm per year, and grain size is 40.3 micron meter. So you can see that, so it end up with the tunnel defect because of the heat input is not sufficient to plasticize the material, so it end up with some tunnel defect. So it is happened in the advancing side. So why make it the defect in the advanced side is that, so normally when your tool is rotated, starting stage is that advancing side. So what will happen if you, whatever the material is pulled out from the advanced side, then it will be steering, and again it will be redeposited to the advanced side. But because of the low heat input, what will happen that the air is not fully filled, so that it will happen or it end up with the tunnel defect. So it is the failure, and the location of the failure is that, so weld nugget. So you can see the weld nugget is failure, and we have to increasing in the order of 200 RPM. And the next we have to conduct the 1200 RPM. So you can see that the pinhole defect in the, you can see the pinhole defect in the retracting side. It is also possible for the inadequate heat input. So what will happen? The weld nugget side, the pinhole defect is formed. But the thing is that only 10, the difference of the strength is the only 10 megapascal. So you can, again, you can increasing the rotation speed of 1400 RPM. The heat input was measured. So 670 joules per mm. You can see that the tensile strength of the joint is the 373 megapascal, and you can see that there is no defect free in the weld region. So after the welding, we can go for the tensile strength. It has to fail in the EMATS region only. There is no defect because of the reason is that because the sufficient heat input, it is suitable for the defect free joints. And you can see that again we can increasing the welding rotation speed of 1600 RPM. The 368 megapascal we can obtain, and you can see that this also 1600 also defect free joints, but the failure is the EMATS region. And you can see the corrosion rate is higher in the 1600 RPM when compared with the 1400 RPM. So you can beyond that at the 1600 RPM, the strength is lower because of the higher heat input. It end up with the kissing pond defects in the radiating side. So that it is mainly happen in the weld nugget area, that is center of the weld. So we can conclude that 1400 RPM is suitable for this 7015 aluminum alloy. So the reason behind that, you can see that the microstructure of all the 5 conditions, the 1000 RPM, it gives the you can see that the grain size is 40.3 micron meter, and the 1800 RPM, you can see that the 23.
The voice is muted, sir.
It's audible?
Now it is audible, sir.
So what will happen? Any disturbance?
No, sir. Nothing, sir. You can proceed.
Okay. So anything wrong, then you can interrupt me. Okay. Right. You can see that again you can study the effect of process parameter, like the effect of welding speed on a mechanical properties, correction rate, and the grain size was tested through this the 707 aluminum alloy. So we can see that we have to keep the 20 RPM, so 20 mm per minute and 40 mm per minute and 60, 80 and 100. You can see that the 60 mm per minute gives the better mechanical properties when compared with the other welding speed. So before conducting the experiments, we had to conduct the trial experiments to fix the levels. for example 20 or 100. So initially we have to go for the trial expense, then we can fix it for the minimum maximum range. Again, we can go for the after welding. We can go for the macro, taking the macrograph, and you can see visually. You can see neck die. You can see the any defect presence in the weld cross section. You can see that the 20 mm and the 40 mm it gives the some of the defects form hole or right. It may be present in the rotating side. It is mainly because of that the excessive heat input. And you can see that the 60 mm per minute, it gives the better mechanical properties and defect-free joints we were achieving the 60 mm per minute. Then you can increasing the rotation speed because of insufficient heat input, so it end up with the tunnel defect in the advancing side. And you can see similarly, you can see that we had to go for to cross-examining the why it gives the better mechanical properties in the 60 mm per minute. Then you can go for the optical microscope. Then we can study the grain size measurement and the size of the grains. And you can see that the grain size of the 60 mm per minute gives the lower grain size when compared to the other welding speed. Because of that, it gives the better mechanical properties. And we have to go for the fracture morphology by using scanning electron microscope. You can see that the 20 mm per minute gives the coarse dimples and the fracture morphology cast cleavage. And you can see that the 40 mm per minute, it is also, you can see that the coarse dimples. You can see that the 60 mm per minute gives the very fine dimples when compared to the other welding speeds. So that the 60 mm per minute gives the better mechanical properties and the lower corrosion in the welding process. And you can go for the another variable like axial force. So because the plunging force is a crucial effect on to study to evaluate the mechanical properties. And you can see that the drill system and harness, right? You can see that the axial force of 7 kilonewtons gives the better mechanical properties, gives the better mechanical properties and lower corrosion rate compared to the other axial force. From that bar chart, you can see that you can easily understand that the axial load of 7 kilonewton gives the better mechanical properties compared to the other one. You can see that again you can test it for the macrostructure. The 3 kilonewtons gives the pinhole defect in the advanced side, and the 5 kilonewtons give the wormhole defects in the advanced side. And you can see the defect-free joints, it will be deteriorated in the 7 kilonewton. It gives also better mechanical properties when compared to the other axial force. So then you can go for the optical microscope, and you can see that the 7 kilonewton gives the grain size of 15.26 grain micrometer when compared with the other, it is maximum. So that it is also 7 kilonewton gives good mechanical properties. Similarly, we have to test it for the effect of process parameter for the shoulder diameter and pin diameter, and tool metal harness also we have to evaluate it. Then from that, so we can conclude that it is understood that the FSW joints are prone to defects like pinhole and tunnel defect, piping defect, slip bond, cracks, etc. It is mainly depends upon the improper flow of material and the lower heat input or higher heat input, right? So we have to optimize and we have to analyze it and we have to do some trial experiment. Then we can fix it for the optimum process parameter. Then and you can see that the better mechanical properties gives the proper process parameter, right? So from that, what I suggest is that this process is mainly suitable for the aluminum alloys. So second, the solid state welding process is that the linear friction welding process. Whatever the previous process, we can see what we discussed is that it is for the, you can do it in the flat specimen, or even though rotary pipe also you can make it with the friction welding process. But you can see that in the linear friction welding process, you can make it the welding only in the asymmetrical specimens. You can see that one by one. So already told that this process is the solid state welding process. It is mainly oscillator joining. So you can, because of that, the combination of the pressure, forging time, and frequency of oscillation, you can make it the non-symmetric components such as aircraft engine blades and disc, right? So you can make it the component with the help of the linear friction welding process. But in this process is that it has to it's depend upon the 4 phases. The first one is the transition phase on the equilibrium phase, and the initial phase, and the transition phase, equilibrium phase, and the deceleration phase. That is called as forging phase, right? The mainly depends upon the fractional heat is generated. So it mainly depends upon the yielding of the interfacial region. So you can see one by one, right? So initial phase is nothing but, so you can keep it the component, right? One is the stationary workpiece and another the displacement. It has to be oscillatory motion. It takes place in the initial phase. And second phase is the transition phase. The transition phase is nothing but you have to apply for the friction pressure, and because of the rubbing of the interface region, what will happen that the friction heat is generated, and it will be the transition will be takes place. And then equilibrium phase. So because of the displacement, so what will happen is that the interface region is plasticized, right? Then you can apply for the forging phase. Then you can, the bonding will be takes place. That one is the, it will happen in the last phase. That is a deceleration forging phase. So this is a machine for setup for the linear friction welding machine, which is available in our manufacturing department. You can see that a small clipping in the linear friction welding process. So one is the stationary and another one is the movable one. The linearly it has to movable. You can see that because of rubbing over the 2 components, right? The friction heat is generated. Then because of friction heat, the flash will be formed, and you can apply the forging pressure. Then the joint will be take place. One is for stationary. You can see that, so very good joint configurations you can make it, or defect free joints also you can have it through this linear friction process. You can remove this flash by using the chipping, or probably in grinding operations. So you can remove the whatever the excess materials. So that is the important for the, so whatever the, not only for the linear friction welding process, even you can go for the rotary friction welding or friction welding process. Flash formats will be, you have to maintain through the proper process parameter. Probably it's a very limited amount of the excess flash will be come out. Maybe you can remove with the help of the external chipping, or maybe you can use it for the grinding operations. So you can see that the stage by stage of the linear friction welding process. So I already told that the first stage is the contact phase. So the one end you have to kept as the stationary, and the another one is the reciprocation, right? So what will happen? One of the workpiece has to be stationary, and another one is you have to give the load, and maybe it has to be reciprocated to towards the linear directions. The proper logging system is required for the workpiece as the proper clamping is required. So because it is to avoid slipping actions. So because of the linear motions, what will happen? The vibratory motions, sometimes some cases it may be slippery, so you have to keep it the clamping in proper way. And second one is the conditioning phase. So what will happen? So it will happen the hyper motion. So because of you can reciprocate this component. What will happen is that the wear will be takes place. That wear the oxides, aluminum oxide, probably whatever the oxides are removed, and then you can give the space. What will happen? The frequency, amplitude, and pressure are the main variables. Because of the amplitude, it will be fixing the length of the reciprocating motion. And third phase is the burn-off phase. Burn-off phase is nothing but the excess amount of flash formations. So in this case, what will happen because of the sharing oscillating moment between the two parts? So the extrusion of the interface materials, it come out as a flash. It is the burn-off phase. And then the fourth phase, that is called as the forging phase. So this phase is the main important role in the final stage of the joining, right? So what will happen because of the forging pressure? So what will happen? The material is both sides. The forging will be takes place because of the pressure applied. So the metal is joined together because of the sufficient temperature and the linear motion of the oscillating motion. So from this linear friction welding process, so we can make it n number of configurations. Maybe it is proven for plate to plate, so it is possible, and round to square also possible, and tube to plate also possible, and square to square combinations also possible through this linear friction welding process. But it took us for the proper clamping devices required for to join this kind of configurations. So the flash development is another important aspects of in this linear friction welding process. So this flash development is you have to control. Already told that it is mainly depends upon the oscillatory motion and applied pressure. So the length of the flash, it is mainly depend on the reciprocating directions. The reciprocating direction is lengthier, then flash will be higher. So you have to control by the proper process parameters. So bonding mechanism. So the mechanism of the linear friction welding process is that. So mainly the viscosity of plastic flow and mechanical intermixing is the two combination of the interface material. The two weld parts, probably it maybe happens the result of movement under the main because of that pressure and substitute forging. So you can see that the metallic bonding will be takes place because of the sharing of electron and the high temperature softened region, adjacent layers of material all mechanically mixed with each other, and uniform stages achieved before completion of the bonding. So you can see that the adiabatic heating caused by high strain rate, deformation at the interface, it improves the softening and intermixing of the matrix surfaces. You can look into the process parameter of the linear friction welding process is that what is the frequency that is called as number of oscillator cycles per second, and ramp up time, that is called as time taken to increase the welding parameters to the required steady state level. And third one is the amplitude. The amplitude is nothing but maximum displacement of the oscillating sample from its equilibrium position, and then friction pressure. Friction pressure is nothing but the pressure applied during the frictional phase of the process. Pressure is calculated by using the nominal of contact at zero amplitude. And then burn off distance or probably it may be called as time or cycles. So possibly factors that trigger the start of the forging phase, and then decay time. Decay time is nothing but time taken to reduce the amplitude to zero at the beginning of the forging phase, and then forging pressures applied during the forge phase of the process, forging time, the amount of time that the forge pressure is applied. This is the and these are the important process parameters which is affect the quality of the weld. So you can control or you can control by seeing the process parameters. The case study for we are getting from the project from the GDRE from the Bangalore, the linear friction welding of air engine materials. In this work, we are using for the titanium 64 alloy, Type 64 alloy. So why they are given this problem is that the air engine inside the power component, the disc and disc are made by the titanium Type 64 alloy and also the Inferno 718 alloy. So probably they are using for the electron beam welding to fabricate this component. So the problem is that electron beam welding is the cost wise is high, as well as the setup cost is more high, so that they are thinking to go for the linear friction welding process. So we are trying to do some work on this process, and you can use it of the Type 64 alloy. Then you can go for some trial expense, and then you can get us the friction pressure 22 megapascal. So we are using for the 5 process parameters like friction pressure, friction time, forging pressure, forging time, and frequency. So 22 megapascal, 35 seconds of friction time, and forging pressure of 11 megapascal, and forging time of 3 seconds, 30 hertz of frequency. You can see that it is not welded, so because of the low head input. You can see that the micrograph of the sample, the flash formation is also not formed, and you can see that. And similarly, you can increasing the friction, reducing the friction pressure and friction time 30 seconds, and forging pressure 5 megapascal, and forging time 3 seconds, and frequency are increasing 14 seconds. Flash formation is good, but still not welded. Flash is formed, but weld is not happened. Then we are increasing increasing the forging pressure. So 3 to 4 second, forging pressure 4 megapascal, and reduce the forging time. So flash formations was very minimum and welded partially. Only you can see that. So partially weld has take place, and then we can reduce the friction pressure and increasing the frequency of 16 hertz. Then you can achieve. You can see that flash formation is not uniform but welded. And then we are trying, again we are trying, right? So change the process parameter, the 25 second and 23 second friction time, and increasing the 30 second and 35 second. So probably some cases flash formation is not uniform but welded. Some cases good flash formations and welded. Some of the cases you can see that flash formation is not uniform but welded. So then finally we can optimize the range of the process parameter. You can see that the oscillating frequency we can less than 10 hertz, maybe it's a less flash formation. Oscillating frequency you can go greater than 18 hertz, right? So more flash will be happen. Then we are limiting for the oscillating frequency. Then you can, after that we can make it a weld. You can see that at 10 hertz, you can see that flash formation is possible, but there is no defects. And you can see that 12 hertz and 14 hertz and 16 hertz and 18 hertz. You can see that interface regions is not fully bonded, but flash formations will be high. You can see that the limits also we can fix it for the friction pressure. Then we can less than 10 megapascals, less flash formation, and in the greater than 30 megapascals, the more flash formation, but slight upset is taking place. Then you can go for the effect of friction pressure of leading friction welding parameters. You can try for the 5 different the friction pressure: 10 megapascal, 15 megapascal, 20, 25, and 30. And then we can go fixing the friction time. So you can see that less than 20 seconds, less flash formation, and you can go for the greater than 60 seconds. So you can see that more flash formation will be takes place. From that limit, so we can do some trial, conduct the experiments 20 seconds, 30 seconds, 40 seconds, and 50 seconds, and 60 seconds. And then the working limits for the forging pressure 5 megapascal and less than 5 megapascals flash formation megapascal. So more flash formation and upset also. From that within the range we can do some experiments 5 megapascal, 5 megapascal, 10 megapascal, 12.5 megapascal. You can see that 15 megapascals, the amount of flash and the regions also deviated. So within that, the combination of the process parameters, we have to fabricate the joints, and we can go for the we have to fabricate the tensile test coupons as per the ACM standard, and then we have to test with the help of the UTM. And you can see that the ultimate tensile strength of the titanium 6L 4V 6LV alloy is the maximum UTS is 996 megapascal, and then yield strength of 926 megapascal, and the elongation is the 13% and reduction in cross section area 30%. Whatever the specimens coupons are prepared as per the EMATS' 25 standards. And you can see that the fracture surface, the most striations in the zone, and the without voids and some kind right, you can long and finer equiaxed grains are present in the interface regions. This is the fracture morphology of the tensile specimen. And then we can take into the optical microscope. So the grain orientations through the optical microscope. You can see the weld center, it's a fine and equiaxed grains, and you can see the TMS region partially the fine grains, and some of the cases you can see that the coarse and long elongated grains are present in the TMS region, and the unaffected base materials somewhat higher than the weld center. The heat affected zone in the you can see that the grain size is higher when compared to the unaffected base metal. So we can take into the optimum condition through the scanning electron microscopy in the various regions. The weld center, you can see that the needleless structures, and the TMS region, so partially needles and grains are presented, and the heat affected zones, unaffected base material. You can see that both are almost the grains are coarser and elongated grains. Then the weld center alone, it shows the needle structures. So you can take into the harness through the weld harness survey through the weld region. So you can see that the weld center, it gives a maximum biggest harness of 450 biggest harness, and the TMS region, it gives the 320 or 330. And then the base metal, it gives the less than 330 or 340. So this is the tables was recorded. Whatever the tensile properties are recorded in this table. So already told that. So we have to achieve the maximum tensile properties of the 993 megapascal and the notch tensile strength of 10,073 megapascal, and the joint efficiencies we are obtaining the 67 and the notch 84. The weld failure region is that you can see that a thermomechanical applicated zone and the notch is weld region. So conclusions from this the linear friction welding work. So we are concluded that the titanium alloys are made by using optimal level of the 20 megapascal, exhibited maximum tensile strength of the 993 and elevation of 8%, and the joint showed the notch tensile strength of 1073 megapascal and the NSR of 1.041, revealing ductile fracture. The linear friction welded Ti64 joints revealed 96.41 and 104 and 66.67 of UTS percentage, and elongation of also parameter also received. So the greater smooth and notch density of joints are principally inputted to maximum refinement of alpha beta grains and at the interface region, and the biomodel microscope is transformed into the Wittmann-Martin structure. This is the reason to achieve the maximum tensile strength. Right. The next one is the conventional welding process. Already the starting itself, I told that the one more the novel techniques in the conventional welding process is that the plasma welding process. So you can see that the plasma is nothing but it is the you can already we know that the matter of the gas, right, and the solid and the liquid. So it is the fourth stage of the matter. So it's called as plasma. So right. So it is another variant of the TIG welding process, right. So in this work they are using for the non-consumable tungsten electrode. That is, it will act as the plasma nozzle. It is mainly maybe red tungsten electrode, and the plasma nozzle is made up on the copper, and the tip of the diameter of the torch is probably around 30 to 60 degree. So already told that it has three variants from this one machine, that is called, one is microplasma. The current range is the 0.1 amps to 15 amps, and then the soft plasma or medium range, it is called as 15 to 200 amps. You can go for the 2 to 4 5 mm thickness of the material. And then keyhole plasma is nothing but over the 100 amps, right? The current range is above 100 amps. It is called as the keyhole plasma. So it is already told that it is similar to the TIG welding process. It has high greater energy concentration and allow higher welding speeds, lesser distortion in this process. So that this process is universally accepted, and the most of the automobile industries or aerospace industries, they are moving towards to usage of this kind of process because it is a high energy concentration energy welding process. The next one is the laser welding process. You can see that working principle of this process is that, so it has two separate regions. One is the plasma region, that is the blue color indicates the plasma tungsten electrode, and another is the plasma region, right? So one is it has to send two gases. One is the plasma gas, and another is the shielding gas. One is act as a shielding gas, and one is used as a plasma gas, right? So you can give the DC power supply, right? So what will happen is the highly concentrated long flash you can see that the weld pool is it's remarkably equal to the laser welding process, right? The plasma is usually operated with the DC. So you can see the dropping characteristics of power source. Because of its unique operating features, it will result the special torch arrangements and separate plasma and shielding gas flows, it's not stabilized with the sine wave alternating current because of the extreme heating of the electrode during the positive half cycle causes rallying of the tip and can be disturbed arc stability. The advantages of this process is that the deeper penetrations and high welding speed, and you can have it greater tolerance to surface contaminations, including coatings. So the drawback of the limitation of this process is that the like bulkiness of the torch, right? There's a because of it carrying the two gases, and it is the tungsten electrode weight and the copper shielding gas, right? That container has the copper, so it has a bulky one. So that is a disadvantage, and making manual welding more difficult. So you can automate it, then it is very easy. Then you can do it manually. It's very difficult to keep the torch to do the weld. And application of this process is that you can go for the sheet thickness of minimum of 0.1 mm, right? You can make it the weld with the help of the microplasma, and then you can the less than of 15 amps current. Even though you can do it for the welding in the wire and mesh sections. And keyhole welding penetrations of plate thickness, you can up to 10 mm thickness can be welded without the filler wire. That is the main advantages of this process. You can see in the boiler manufacturers, right? So they are the boiler drum, right? Even though the superheaters and water valves, right? The tip of the 304H tubes wall thickness is nearly 12 mm thickness or 13 mm thickness, because they are recently they are fabricating the tubes in the inconel materials, probably in the 625 tubes. So the tubes is used for, maybe in some cases they are using for the 718 tubes also, because the advanced ultra supercritical boilers they are using for the 718 tubes. So that cases you can go for the through this the plasma welding, like keyhole welding process. So another case study for the plasma welding process. In this work we are using for the inconel 625 alloy. So this alloy is mainly used for the air engine application. So because of the dash to withstand the temperature of the 650 degrees centigrade, where the working temperature inside that engine is 600 degree. So that in inconel 65 is mainly used as the high temperature applications like the rocket, right? Engines, gas turbine engine, right? So it is, and also it is also good as a stress structure properties and good resistance to corrosion and oxidation are the major important of this alloy. The origin of the problem of while they are using as this material is that, so all of we aware of that the lava phase formation. So what will happen that this when you using this process, not this process, in other process like the conventional welding process, even TIG or right. So what will happen is the lava phase will form in the during the welding. So it end up with the crack initiations because of the alloy segregation a little bit takes place. The niobium is the matrix and hinders the effect of double prime, comma double prime precipitation will be occur. So to avoid these issues, it end up with the porosity. Then it will be crack will easily form. So another issue is that hot cracking in the fusion zone. So immediately because of higher heat input, so during the welding it go for the 180 degree centigrade. What will happen because of higher heat input? It segregates the elements in dendritic liquid. It will again it will be forms at the lava phase in the interdendritic region. It impairs the ability of the nearly solidified weld metal to withstand the tensile stress that occur during the cooling part of the weld cycle. So it is mainly depends upon the lava formation and the higher heat input. Higher heat input, it is depend upon the hard cracking in the fusion zone. And third important issues is that the microfissuring and the liquidation cracking in the heat affected zone. So what will happen? So because of the low temperature in the hydrotic form, hydrotic film is formed in the along the grain boundary of the heat affected zone. The coarse grains are most sensitive to microfissuring. Because of that, the low temperature melting of grain boundaries results from the liquidation of niobium enriched tungsten carbide or type of carbide salvage phase and during the rapid heating of the heat affected zone. So to avoid this kind of issues, then you can solve or you can go for the low heat input process that is called as that is suitable for the soft plasma. Right, the soft plasma you can go for the working temperature of the ampere of the 15 amps to 100 amperes, right? And also we are providing the shielding gas. So and also the arc is, you can see that the thick arc, you can see that the wider the arc is wider, but you can see the plasma arc welding. It is a long and narrow opening of the arc is generated so that it will be suitable for the Inconel 65 alloys. The objective of this work is to optimize the process parameter by using the RSM. So probably they are optimize the bead geometry, bead characteristics of 65 alloy, and then he has to reduce the fusion zone, heat affected zone width, and fusion zone area, heat affected zone area, and SDS and volume fraction of lavage phase, short dented cone structure, right? And then to increase the depth of penetration, fusion zone hardness, and heat affected zone hardness. So the chemical composition of the 65 Inconel alloy is that, so it has the base metals, it has chromium 22.7 and molybdenum, and iron is 9.5 to 1. The mechanical properties that you can see that Inconel 65 UTS 938. You can see the base metal microstructures. It has gamma matrix and annealing tunes are present in the base material. And similarly, you can take into the SEM image using the scanning electron microscope. This is an experimental setup of the plasma welding machine, which is available in our department. So it is the model of Transtick 4000 and the model PM10. And this machine was having two kind of cylinders. One is a shielding gas, and another one is using as a plasma gas cylinder. And this is a power control unit. This is a plasma module, and it is a power source. It is a Transtick 4000 DC direct negative. And you can see that this is a plasma torch, and so this is a welding lathe. So you can make it the tubes or pipes. You can go for this welding lathe. Then flat specimen also it's possible through its automation. So we have automation method also available and coupled with the plasma welding machines. So you can see the close-up view of this welding. So this also we have to do it for the flat specimen. So after experimentations, then you have to extract the specimens for macrograph, microstructure, and micro study, and you have to make it the mountings. So whatever microstructure you can go by using the stereoscope microscope. And the optical microstructures we can take into through the optical microscope. And the harness, we have the Shimatsu Vickers micro harness testing machines. And the so this work is we have to measure we have to optimize for the fusion zone width and the width and height, as well as the secondary dendritic arm structure. So there's a secondary dendritic arm structures calculated using this formula, that is a lambda 2 equal to L by N. L is nothing but total length over the measurement. This is the total length. And number of secondary dendrites. Each one is the secondary dendrite. We have to measure this and the dendrite's length also, and also the size. So before that, the conducting the regular experiments, so we have to go for the preliminary experiments. Then we have to find out the limits for the minimum, maximum. Then we can fix it for the welding current less than 60 amps. So you can see that. So lower current, it's lack of penetration of the weld area. So similarly, you can go for the greater than 80 amps current. It may be burn through occurs due to the high current. And welding speed, we have to go for the less than 110 mm per minute. So it gives the lower welding speed, causes wider weld beads. And you can go for the greater than 150 mm per minute. So higher welding speed causes welding discontinuities. Then plasma gas flow rate, we can go for the less than 0.8 liters per minute. It gives the lower plasma gas flow rates, causes improper weld beads, and greater than 1.2 liters per minute. So you can see that the some of the blows are burns through the weld center, right? And similarly, arc length, you can fix it for the less than 3.5 mm. So because of the arc length, so shorter arc length, what will happen? It has the risk of the nozzle. So you have to come to the greater than 3.5 mm. So and then the maximum of 5.5 mm. So what will happen that the widens the weld bead and the leads to increase, and contamination will be takes place. So based on that, we have to cut the minimum maximum range. In this work, we are using for the 4 factors 5-level center component design. Based on the design, so we have to conduct 30 set of experiments. Each conditions we have to study for the 3, and the average will be taken into the account. And then we have to measure the fusion zone width and heat ablated zone width and fusion zone area, heat ablated zone area, and depth of penetrations. So you can see the macro graph to measure the fusion zone area with and other. Likewise, we can measure the 30 set of macros, and we can go for the ANOVA test for the bead geometry. So you can see that from that what we have to observe from this work is that, so from that the F value, we can conclude that welding current is so you can see that the F value is 10 to 3.4. That is a highly influenced parameter when compared with the plasma gas flow rate, then the consider arc length, then finally the welding speed, right? So the lack of it is normally it gives the not significant. On all the probability values are less than 0.05, so it is significant in the test matrix. So this is the bead characteristics values of 30 set of experiments, the secondary dendritic arms size. So we measure the STS and the volume of fraction of lavage space also measured, and the fusion zone hardness and heat ablated zone hardness. And you can see that the macros measure the SGS, you have to measure according to these microstructures. That is a 26 set of the microstructures measure the SGS value, and then you can go for the ANOVA test for the which is the significant factors, and some of the square terms and main terms are measured, and all the probability values are less than 0.05 because we are testing the 95% confidence interval level. Then we are developing the empirical relationship for this equation is mainly used for to calculate the whatever the output response, right? We have to measure it, and without conducting experiments, easily you have to substitute the values in the suitable parameter in this equation. Then you can easily find out the output response of response. For example, you can say that efficiency and width, you have to measure it, and then you can substitute the value of the D and S, G, D, then you can get it the value from this equation. Similarly, we have to develop for the other output responses. It is mainly used for the it is mainly used for the design engineers, welding engineers. Then we have to develop for the secondary tentric arm spacing, SDS, and volume of fraction Lavi space also measured, and fission on harness, and the harness, harness, we have to calculate it through this empirical relationship. This is a graph for the 2-dimensional and 3-dimensional graphs, right? So from that graph, 2-dimensional graph, what we have to understand is that, so interaction between the welding current and welding speed. So if your two factors are interaction takes place, so you can see that the efficiency and width will be width is the 70 amps, and the 130 welding speed, it gives the efficiency and width of the 5.02. Similarly, the plasma, the interaction effect of the welding current and the plasma gas flow rate, the welding current is 70 and the plasma gas flow rate is 0.97, nearby 97. It gives the prediction will be give the 5.02. The 3D graph shows the surface flats, the top region, so the interaction of effect of the welding current and welding speed. The top of the apex, it gives the maximum fission zone width. Similarly, we have to develop for the other process like heat affected zone width and fission zone area, and the heat affected zone area and depth of penetration. And then this is for the graph between the welding current and welding speed for the secondary dendritic arm structure. That is for the develop for the volume fraction of Lavi space, and that is for the fusion zone harness. That is for heat affected zone harness. So finally, we have to go for the multi-response optimization. So the main ultimate aim of this work is that, say, we have to minimize the fusion zone width and the heat affected zone area. The remaining that, so we have to maximize, right? You can see that some cases the current in drain, and you can output response. You can see that the efficiency with this minimum, and the heat affected zone we have to target for, it is required for the 2.4 mm. The other rest of the heat affected zone area is also minimum. The rest of the other output responses are right maximize, and the SGS we have to maintain as the minimum. In this criteria, for example, SGS minimum, and then heat affected zone is minimum, and then efficient zone is the minimum, and the heat affected zone width is we have to target as 2.4 mm. Within that, so which parameter the current or the welding speed or plasma gas flow rate or construct length, right, which gives the correct, right? So that we have to identify through this multi-response optimization. So from that, so whatever these results we are obtained from the design expert software, that is the DOE software. So from that, the software has suggested that the welding current of 69.73, welding speed of 131.86, and plasma gas flow rate 0.96, and arc length of 4.72. The predicted efficient zone width of 5.02, heat affected zone width of 0.310, and efficient zone area of 7.45, and heat affected zone area of 1.58, and depth of penetration of 2.32. So this is the software given value, and we have to conduct the experiment confirmation test. Then whatever the same parameter as fixed, and we have to conduct the experiment, and almost we are obtaining the results, and the percentage of errors is less than 5%. So it is acceptable one, and similarly we have to go for the SGS value and vision zone honors and volume fraction level space, and we are conducting the experiment, and then almost all the values are less than 5% of error. This is the graph for the multi-response graph. From that, you can see that the efficiency zone with the 5.2 or 0.31 efficiency area. Within that, the optimum parameter we are obtaining in the graph. So conclusions. So in this work, titanium 64 alloy thin sheet we have welded through this process, and the plasma inconel 60Y, it gives the welding current of 69 amps and welding current of 132. So has produced minimized weld bead of width of 5.25 mm and good penetration of 2.4 mm, and reduced fusion zone area of 7.6 mm square, and SGS of 31012 micrometer, volume fraction of live space of 5.900. This gives better one, and the parameters is govern the heat input changes during plasma welding, namely welding speed followed by welding current, are found to have abdomen influence in increasing in increment and decrement tendencies of weld characteristics such as weld bead width, penetration depth, fission zone area, and SGS and volume fraction of lave space. Plasma gas flow rate is also found to influence selective welding characteristics such as penetration depth, whereas constricted arc length holds the least influence of all. Thank you. So any doubt, you can interact with me.
Participants, you can unmute and ask questions to the expert right now. Yes, sir. So the expert member over here, I will start with the question here. Sir, we designed this faculty development program to cover various emerging technologies, mainly concentrating on the sustainability factors. So your role as developing novel material and dissimilar material, particularly joining, is very, very highly pronounced as per your publication and your research progresses. So in what way your further research can be taken through various research scholars towards sustainability development, sir?
So sustainable development in the sense, right? So recently, right? So you can go for the some of the carbon fiber reinforcement, right? So you can see in the aerospace industries, so they want to know that, so the lightweight structures, right? Lightweight structure in the sense you can add with the carbon fiber with metal, and then they are asking for the develop for the new welding technology for the to join the carbon fiber with probably the laminated structures. Carbon fiber with the thin sheet of aluminum or titanium, likewise you can make it the laminated structures. So whether you can go for the diffusion bonding or probably laser or something, you can go for.
And regarding welding challenges, when biomaterials are incorporated, what is the challenges one might encounter during the high temperature process such as this welding?
Actually, biomaterial in the sense, can you explain which material?
Like you told, like plant fibers or biochars or anything that is impregnated for improving the properties of material like composites.
So better you can go for the diffusion bonding.
Yes, sir. Thank you, sir. Thank you, sir. I think your questions, your answers to the questions, better than this earlier explanation of whatever research you have taken. I think you have completely given this wholesome of whatever you have taken from right from problem statement to conclusion. Everything is clearly understood by the audience over here, and people may not have any doubt after seeing your clarity of instructions here. But in case they have a doubt regarding connecting with you for any other program as a resource person, or maybe for inviting you over the online meeting, may I share your details, sir, like email ID, phone number?
Oh, yeah, no problem, sir. No problem. You have it, my mail ID?
I have it, sir.
Okay.
I'll post it in the forum right now.
Okay, thank you.
So that people may know it.
And also we have facilities, right? Whatever the facilities, right? So we have sophisticated instruments. Maybe you can feel free to contact.
Yes, sir. So I'm posting Dr. Rajakumar's email ID here. Anyone who wants to contact him, please take note of this. So I should be thankful for your patient delivery of wholesome of whatever research you are doing, sir. We have deep respect for your efforts to bring the metal joining. To your information, sir, we also set up one cold metal transfer.
Oh, you have CMT, Furnace,
yes,
right?
Sir. Yes, in Furnace, the same machine what I have been telling.
Okay.
And we are finding difficulty to people to make people convinced that our facilities to be used for research purpose. We have research center, institutional research centers.
Okay.
So if you know anyone who can do the work nearby, also you can refer to us. Other than CMT, yes. Sir.
From that CMT, you can do a lot of work. Where are additive manufacturing? It's advanced booming technology, right? You can do it many work on the CMT process.
Okay. Okay. So not only dissimilar metals, the same setup can be used for some other purpose also.
Yeah.
Okay, sir. Okay, sir. I think our research scholars, our participants over here will take your points and do it for some kind of research proposals also in future, whatever they wanted to do, explore. Also, they will improve on the publications based upon your findings, taking it as a citation. If it is possible for you to come over to Chennai, sir, you please make a point to visit us.
Yeah. One day I have to make it arrangement, make it a meeting in our campus. Probably yes. I will come.
You're welcome, sir. You may be possibly make a contribution to your academic council also. Okay. I'll try to give your name for recommendations.
Okay.
We'll be happy to have you in our academic progress.
Thank you.
So, as a formal thank message, I want to convey once again the deep respect and efforts to bring all the concepts and metal joining related doubts that would have been cleared by this session, I think. And your deep knowledge of manufacturing process has been discussed to all the participants. And we will also take in the other direction, like how green composite production, how the other kind of new material can be possibly, with your possible points, we can make it very viable for the development of the sustainable growth. So thank you very much, sir. Thank you for joining the session, sir. Thank you.
Thank you, Muthukumar, for giving a nice opportunity to share our findings.
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir. The speaker will be leaving, sir. Others, please stay in the session. So as we are progressing to the next session, participants, they have any queries, they can post for whatever session where they had any kind of doubts. I'm here to bridge you the gap between the speakers and yourself. Number of sessions they have shared as these slides also. So if you want such kind of material as well as this contact details of the persons, you can even interact during the session. I'll make a note of it, or the organizer's email ID is posted in the formula. Myself, Tukumar at welltechmultitech.org, you can contact. Has anyone got any queries? Any questions for clarifying your doubts with the next speaker? Thus, to introduce with the speaker, we have Dr. E. Balaji. It's ready to start the session in a few minutes. Our next session's speaker is going to be Dr. M. Dinesh, Chief Technical Officer at Avionics Drones, the local group of companies known for its impact on drone technologies and the related sustainable development for the agri-tech as well as the other kinds of transport related things done through the drone technologies. So you can prepare your questions for the interactive session with the industry expert over there. Feel free to interact during the session. I'll keep muted for the next 10 minutes. We'll join after 10 minutes. Please be joined in the session. Thank you.